Hi guys, welcome back to my channel Pirai Academy. In this series of Zoho interview question, today we are going to see about a question called 0-1 knapsack problem. So you will be given n items, each with a specific weight and value, and a knapsack with a capacity of W. Okay. The task is to put the items in the knapsack such that the sum of weights of those items will be always less than or equal to the capacity of that knapsack, and the sum of values associated with them is maximized. You can either place an item entirely in a bag or leave it out entirely. Also, each item is available in single quantity. So they have clearly stated that we want to take each and every item entirely, or we want to leave it as it is. We cannot take any item as fraction. For example, if an item of 5 units weight is there, then I cannot take 2 units of weight from that thing or that item. Okay, I can take entirely that 5 unit, or I cannot take anything. Okay, I don't take that. Fine. Now just see this example. If the capacity of the knapsack is 4 and values are given like 1, 2 and 3, and weight or respective to those values are 4, 5, 1, then what is the best answer I will be picking? So I will be picking only the weight 1, because weight 1 is less than or equal to this capacity and its value is maximized. It is 3, right? If I take this 4, the weight of 4, then the value will be only 1, which is less than 3, right? Whether I can take weight of 5? No, because it is exceeding the weight, right? Okay, see the second example. Here the capacity is 3, but all the weights are greater than 3. So I cannot take any one of those items. Okay, so the answer will be 0. Now the capacity is 5 and the values are like this and weight are like this. Then what is my best answer I will be choosing? First of all, just see here. For this weight of 5, I can take this weight 5 alone. If I take that, it will be only 10. Or else I can take only this 4 alone. If I take that, I will be getting a weight of 40. If I take this 2 and 3, okay, I can take it because it will be 5. 5 is less than or equal to 5, right? So if I take this both things, then it will be something like 30 plus 50, which is equal to 80. 80 is the best possible answer I will be getting, right? So I will be returning the 80 as my answer. So it should be a maximum. Fine. Now let us proceed with what is the concept behind this. Okay. So basically from this itself, we can clearly understand that we want to take a best possible answer, right? So to take the best possible answer in those examples, the logic is we want to take as much as items we can. Can you understand this? Right? So for the second example, for this example, right? For this example, I have taken as much as weight I can, right? Because sorry, as much as item I can, because I took this 2 and 3 instead of this 5 and 4. When I can take as much as items I can, whenever I am taking a weight of lesser values. Can I understand this? If I take this 5 is the largest value in this, right? So that's the reason why I cannot take any other item. If I take this 4, I cannot take any other item. If I take this 2, I can take also this 3. Can you understand this? So I want to take a lowest weights as possible such that I can take as many items I can. So from this example itself, I can clearly say that the logic we all think will be like, I will be just sorting this array respect to this value. Okay. For example, I will be taking this as my example. Okay. So let us take this as my example. Now just to see here, if I sort these both in the ascending order, then the weight will be something like 2, 3, 4, 5. And its corresponding value will be like 30, then 50, then 40, then 10, right? Now what is my capacity? My capacity is 5. Okay, now I am going to traverse. So if I traverse here 2, whether I can take 2, weight 2. Yes, you can take because it is less than 5, right? So it will be become 3. Now the capacity will be become 3 and the result will be something like 30 because we can take this value, right? Now go to the next thing. It is what? 3. Whether I can take 3? Yes, you can take 3 and make this as 0. And whether this will be my result? Yes, you can add this in my result. So it will be something like 80. Okay. Now when I am going here, it is what? 4. 4 is greater than 0, right? So we cannot take that. So stop here. Stop here. So now what is my answer? It is 80. Okay. Fine. But whether it is work always, whether this algorithm work always. So this algorithm is called greedy algorithm. And its time complexity will be going to be O of n and space complexity will be O of 1 for the traversal, but we are just sorting it, right? So here comes n log n and space complexity will be n. So this is my time and space complexity analysis for this greedy approach. But whether this approach is correct, first of all, no, it is wrong. It is wrong. I will be telling you with another example, okay? So here comes another example. So we want to just apply the same greedy algorithm here also to know what is the mistake we have made. Okay, let me apply this algorithm here. So first of all, I want to just sort the weight in ascending order. As you see here, it is already in ascending order, right? Now, whether I can take this one as my first thing. Yes, you can take because weight is already what? Capacity is 5, right? 5 is greater than or equal to this one. So if I take this, then 6 will be as of now in my hand. Okay. Now go here. So this will be become what? 4, right? Now 2. Now whether 2 I can take this. Yes, you can take the weight of 2 because your capacity is 4. 4 is greater than or equal to 2, right? So I can take this and here comes what? 10. So 6 plus 10 which is equal to 16 and it will be becoming what? 2. Now go here. It is what? 3. Whether I can take this 3. No, you cannot take because our capacity is 2. How can you take this 3? So stop here. Stop here. So what is my answer? It is 16. But if I take this 2 and 3, this 2 and 3, then my answer will be what? 22. 22. So 22 is greater than the 16, which means currently our approach, the greedy approach, is wrong. You may ask why the greedy approach is wrong. We have spent logic in our test case correctly, right? Then how come it is a wrong? No, because here I can pick an element entirely or I don't pick that item, right? So in that case, this greedy algorithm will be losing its uniformity concept. Okay, so that's why we are going to what? A recursion backtracking approach. I'm just telling this entire greedy approach just to realize you that this greedy algorithm will be failing for some cases. Okay, whenever there is non-uniformity concept comes, then we want to go for the all combinations, like whether I can take this item or I not take this item. Okay, in that scenario we will be switching over from the greedy approach. Okay, so since the greedy approach fails, we are going to what? A recursion backtracking approach. Fine. Also, I will be showing the code for this greedy approach, or I will be giving in the description. Just go and just search for it. Okay, so it is not mandatory, but also know this greedy approach is incorrect approach for this problem. If it is for a fractional knapsack question, which means you can take a small quantity also. Like if there is 5 unit weight, you can also take 2 unit weight or 3 unit weight. Okay, then it is allowed for the greedy approach. Greedy approach will be the opt approach there because it follows the uniformity concept. But here you want to take entirely or don't take it. So here you want to apply only the recursion. Just understand this. Okay, fine. Now, how can I apply a recursion? First of all, a recursion is just a function call, right? Okay, I will be writing a function. Now, what are all the parameters that are going to affect my function? So basically here I want this capacity, right? Capacity. Okay, so I will be putting this W. And also I want to traverse each and every elements, right? So I want to put a index. So these are the two parameters I will be encountering in my recursion. Just hold on. While I am explaining the recursion tree, you will be absolutely knowing why I am putting here index and the capacity. Okay, fine. Without delay, we can get into it. So initially function of 0, 5, which means I am at a 0th index. Okay, with the capacity of 5, I am moving towards the right. Can you understand this? Can you understand this? So what is my current weight? So current weight array is 1, 2, 3, and my current value is what? 6, 5, 12. Just understand this. Okay. So initially I am here at the 0th index. Okay. Now I can either take that weight or I cannot take that weight. So it is like take, not take. Okay. Fine. Now if I take, then what will be my next recursion call? It will be, if I take this weight, then its value will be going to be added, right? So value will be added. Then next recursion call going to be to the next element, which means 1, comma, what is my current capacity? It will be 5 minus 1, because here the weight will be 1, right? So it will be 5 minus 1, which is equal to 4. Can you understand this? This function call represent what? I am currently at the index 1 with a capacity of 4, going towards the right to get the maximum value. Can you understand this? Fine. Now similarly I will be not taking it. If I not taking it, then 0 plus, because no value. If I don't take any item, it will be 0 value, right? So 0 plus function call of first index with a capacity of 5. Okay, fine. Now next thing, from this first index, I can either take the first index or I cannot take that first index. So currently I am here. Okay, I can either take this 2 or not take this 2. If I take this 2, then it will be something like 6 plus, what is the value of 2? It is 10, plus what is the function of 2, comma, if I take the 2, remaining will be 2, right? 2. Can you understand this? Yes, it is simple, as much as simple, right? Okay. Now if I don't take it, it will be remain 6 only. 6 plus 0, because I not take it, right? Plus function call of 2, 4. That's it is. You can just return the 4. Okay, I am not taking anything, so capacity will be remains same as here. Okay. Now again come here. Here I can again take and not take, right? If I take 2, then it will be something like 10 plus, go for a function call of second index with a capacity of 5 minus 2, which is equal to 3. Okay. If I don't take, then 0 plus again 0. Here 1 0, and now also I am not taking, right? So 0 plus 0, function call of 2, 5, because I haven't taken anything. Okay, fine. Now the next will be, I can either take the index 2 or I don't take index 2. If I take index 2, this 3, okay, then I should having a capacity of 3, right? But here my capacity is what? 2. So I cannot take the 3. So here my recursion call will be cancelled out and returned back as 0. Can you understand this? Yes. So I cannot take. Okay. Now if I not take it, it will be something like 6 plus 10 plus 0 plus f of 3, 2. The capacity won't change, but our index will be plus 1. Okay, fine. Now similarly here I can take, again I will not take. If I take, it will be like 6 plus 0 plus, if I take, it is what? 3. 3 is less than 4, that's why I am taking. This capacity 4 is greater than 3, that's why I am taking. And if I take it, the value of 12 will be added. So 6 plus 0 plus 12 plus function call of 3, 4 minus 3. The current weight will be 1. Hope you understand this. Okay. Now, if I don't take it, then it will be like simply 6 plus 0 plus 0 plus function call of 3 comma 4 as it is. Okay. Here also similarly, I can either take or I cannot take, right? If I take it, it is what? It is 3. That's why I can take it. Here it is 2. That's why I cannot take it, right? So here it is, we can take. So if I take, it is something like 10 plus 12 plus function call of 3 comma 0. 3 minus 3 is equal to 0, right? Now, if I don't take it, it will be something like 10 plus function call of 3 comma 3. Similarly, if I here, I can take it, right? If I take it, it will be something like 0 plus 0 plus, what is the 3's value? It is 12, right? So 12 plus f of 3 comma, here it is 5. So 5 minus 3 will be 2, right? If I don't take it, I can write here. If I don't take it, then it will be something like 0 plus 0 plus 0 plus f of 3 comma 5. Okay. Okay. Now listen this carefully. Now you want to listen this very carefully. Okay. So here f of 3 comma 2 represent what? I am currently at index 3 with a capacity of 2. Whether there is any index 3? No. So whenever my index is equal to the length of the weight array, then I want to just return 0 because there is nothing item left over. So I will be returning what? 0. So here comes what? 0, right? So 6 plus 10 plus 0 will be what? Will be of 16. Now here similarly this also will be 0. So here I will be yielding of 18. Here also it will be 0. So here I am yielding 6. Okay. And here also I will be yielding a 0. So here comes at 22. And here also it will be 0. So it will be 10. And here also it will be 0. So I will be yielding 12. And here also it will be 0. So I will be yielding 0. So among this, what is the greatest or what is the maximum? It will be 22. Okay. So basically it will be like returning the values, returning the maximum values. Again, I will be drawing the recursion so that it will be recursion tree so that it will be more clear. Okay. Just focus on this. It will be quick recap. So f of 0 comma, here comes what? Initial weight. Okay. What is the initial weight? It is 5, right? So I can either take the first index or I cannot take, I can either take the 0th index or I will not take the 0th index. If I take the 0th index, it will be something like 6 plus f of 1 comma, then what is the first index weight? It will be 1, right? That's why we can take it. Okay. So let me reiterate here. Weight array will be 1, 2, 3 and value will be 6, 10, 12. Just remember this. Okay. So here comes what? From the first index of capacity 4. Okay. Then it will not be going here in a practical. In practical, it will be not going here. For your understanding purpose only, I am just drawn like it will be going here. But in real time, the recursion call will be always like TFS traversal, not BFS traversal. I will be telling you how it will be going in a recursion call. Okay. Now again, it will be take and not take, right? Take and not take. It will be first going to the take only. Okay. So now it is at the first index. So now it is 2. Whether I can take 2? Yes, you can take 2. If I take 2, then it will be something like 10 plus f of 2 comma 2. Right? Now again, whether I can take my second index? No, the second index is what? Second index 3. So I cannot take 3 because my capacity is 2. So it will be null and it will be returning 0. It will be returning 0. Now only it will be going for not take. Can you understand this? Once it finishes the left subtree or left side tree, then only it will be coming to the right side. Okay. Always it will be like this only the recursion. I am just giving you a BFS traversal just for your understanding purpose. Not it will be not a practical. Okay. Now if I don't take it, it will be something like 0 plus f of 3 comma 2. Okay. Then again it will be proceeding Okay, it will be proceeding, and here comes what? Here comes 3. That's why it will be returned as 0. Can you understand this? Yes, yes. Now it is replaced as, this entire function is replaced as 0. So 0 plus 0 will be 0. So here comes 0. Now whether this 0 is maximum or this 0 is maximum, among these both are 0, right? So this entire function is replaced as 0. So 10 plus 0 is 10. So this will be returning what? 10. Can you understand this? Yes. Now only this function will be going for a not take recursion call. Okay, it will be not taking, right? So it will be something like 0 plus f of 2 comma that real time capacity, and it will be again going for a left subtree called take. If I take it, then it will be something like I want to take this last index. That's what the second index, right? So it is 3. So 3 is less than 4. So if I take this, it will be something like 3's value is 12. So 12 plus function call of 3 comma 4 minus 3 will be 1. So 1. Okay, again it will be going, and it will be like a last index. So it will be returning what? 0 here. Okay, and then this entire function will be returning 0. Okay, so 12 plus 0 will be 12. So it will be returning here. Now only this will be going for the not take. If it is going for a not take, it will be 0 plus f of, here comes what? Here comes 3 comma 4, and then it also go here, and it will be returning 0, and this entire function will be replaced as 0. 0 plus 0 is 0 again, and it will be returning 0. Now just listen this carefully, whether this 12 or this 0 is maximum. This 12 is maximum, so this function call will be replaced as 12. So 0 plus 12 will be 12. Yes, now it will be returning what? 12. Let me take any other color. Now it will be returning what? 12. Now just listen, whether this 10 or 12 is maximum. 12 is maximum, so this function will be replaced as 12. Can you understand this? Yes. Now this function is replaced as 12, and 6 plus 12, which is equal to 18. So hats off, now my left recursion calls value is 18. 18 is my maximum among the left subtree. Okay, for your realization, I will be going here. So see here. So this 18 is present in where? In a left subtree. This left subtree, right? Can you understand this? Can you understand this approach? Now similarly, I will be executing for the right subtree. If you understand this right subtree's answer, you can just skip this just tutorial. Okay, if not, you can see. Okay, if I don't take the 0th index, then it will be something like 0 plus f of 1 comma capacity as it is. So here I can take, right? Here if I take, then it will be something like I want to take this 2, right? It's kept, its value will be 10. So 10 plus f of 2 comma 5 minus 2 will be 3. Okay, again I can take what? I can take the second index because here is 2, right? So I can take second index. If I take second index, it will be 12. So 12 plus f of 3 comma 0, right? Again it will be going here, and the index is already 3, so it will be returning 0. Now 0 plus 12, which is equal to 12, so it will be returning what? 12. So this entire function will be replaced as 12. 12 plus 10 will be given back or returned back as 22. Okay, again here comes another recursion call. So this recursion call is for not take. If I don't take it, it will be 0 plus f of 2 comma 5 as it is. Okay, now I can take this second index, right? I can take this second index. So if I take this second index, then it will be something like 12 plus f of 3 comma 5 minus 3 will be 2. Okay, again it will be going here, and it will be returning 0, and this entire function will be replaced as 0. So 12 plus 0 will be returned as 12. Can you understand this? Now again if I go here for a not take, then it will be something like 0 plus f of 3 comma 5. So this again go here and return back as 0, and it will be returning back 0 plus 0 will be 0, and among this 12 and 0, what is the maximum? 12. So 12 will be returned back from this function, because 12 plus 0 here 12 plus 0 will be what? 12 only, right? Because this entire function will be replaced as 12. So 12 plus 0 will be 12. That's why I'm just returning 12. Now I want to check whether this 22 or 12 is maximum. My 22 is maximum, right? So this entire function will be replaced as 22, and 0 plus 22 will be 22, and in my right subtree it is 22, and in my left subtree it is 18. So 22 is my best answer. So my f of 0, 5 will be returning as 22, which means it implies that 22 is the maximum number of values we can take with the capacity of 5 from the index 0. So that's what this f of 0, 5 represent. Now hope you understand the entire recursion calls and how the recursion tree is built. Okay, so always remember the recursion tree is DFS traversal, not a BFS traversal. Okay, now let us see the code. Always prepare a Java code for Zoho interviews. Okay, let me comment this out. So this is the greedy code. Okay, however it is incorrect, but still you want to know it, right? When you are applying for an interview, they will be asking why this is not possible. In that time you want to say that uniformity concept. Okay, fine. Now here I want to call the helper function with the 0th index with a capacity. Okay, now this helper function will be first checking in a base case, like if the current index is equal to the value dot length. If it is so, then it should be returning 0 there itself. Okay, if not, take will be initially 0. If the current index weight, okay, is less than or equal to the capacity, the current capacity, then only I want to take that value, okay, plus I want to go to the next recursion call with the capacity minus the current weight. Okay, next not take is equal to just to go to the next index without changing anything in the capacity. So it is basically like I want to take one item and I want to don't take one item. So this is like a combination. Okay, and at last I will be returning the maximum among the take and not take. So this is going to be your recursion code. Okay, so this code is huge time complexity. Why? Because of its exponential manner. So it will be something like O of 2 power n, because for each and everything, for each and every elements, okay, it will be splitting like take or not take. Okay, so two ways. So for n elements it will be 2 power n, and space complexity will be O of n. Okay, because we are having a stack space like this. So this is the entire stack space. So this stack space will be absolutely equal to the n value. So this is going to be my time and space complexity. So to optimize this, we can use a efficient approach called memoization. So this memoization will be going to store each and every values in the hash map. Okay, and whenever that value is repeated, it will be just taking the value from the hash map and providing it. Okay, for example, in some cases there may be like we already found f of 3, 5. Okay, in some other branch again that f of 3, 5 may occur. If it occurs, then also it will be going down to find what is the maximum among it, right? But instead of that, already I found this, so I will be keeping this in some memory, so that while again it is encountered, then from here I will be just giving here the result. Can you understand this? Yes. So basically anything here? No, here we didn't encounter anything, but when you are going for a more number of elements, then you will be encountering this. So I will be showing the code so that it will be more clear for your memoization technique. So just a minute. Yes. Now, so this is going to be your memoization code. It is just 2 lines. You want to add only 2 lines. Just listen this carefully. So here comes, this line is same as the recursion code. So here key will be I plus hyphen plus the capacity. Okay, so this is the key. Okay, and I am going to check whether the key is present in my hash map. If it is present in my hash map, I will be just returning the key value. Okay, so this is the extra line we have added. Okay, let me mark here. So this is the one of the extra line added, and this is the one of the extra line we have added. And another extra line we have added is this. Okay, here what I am adding for that current key means what? This, the corresponding index with the capacity W. For that I want to just put a result. So result means what? The value, the maximum value I got as of now. I will be putting that as the value. So this will be my key value pair. Can you understand this? Can you understand this? See here, in recursion tree we have encountered f of 3, 5. Okay, again in some other part of that recursion tree I am again encountering 3, 5. Then why should I go down for that 3, 5? Okay, that f of 3, 5 and find out what is the maximum answer. Okay, instead of that, already I encountered that same functionality. So I just make this to store in the hash map. Okay, and if that exactly that 3, 5 is again repeating, okay, then I will be just taking the result from the already existing that function call and I will be giving to the current function call. For example, if I encountering this 3, 5 already, okay, then I will be storing like 3-5 is to the result as some result. Okay, and again in some part of the recursion tree, again this is encountering, then I will be checking whether this 3 and 5 are present. Yes, it is present. Then I don't want to go down and search for this. I will be just taking this result and returning here. So this result will be written here. Now hope you understand why we are using a memoization technique. Okay, so this is the hash map memoization technique, and here the time complexity will be here like n into w, like n into w into log of nw, because we are also taking the weight, right? Weight and the index. So it will be something like this, and here also it will be into w because of the hash map. Fine. So here why we are getting this log n into w? Because we are just using a hash map for retrieval and putting some element, right? So we are just accessing some element and putting some element as you see in the code. Okay, so to get rid of these things, okay, which means to get rid of the log n and convert it into a constant time, I am going to introduce a matrix. Why? Because in matrix the access and the putting time will be of O of 1. Okay, here two parameters are affecting my recursion call. That's why I am using a 2D array. If only one parameter is just affecting my recursion call, then I will be using only 1D array. Can you understand this? So I am going to use a memoization using matrix. So let me take the matrix here. Fine. Now this is going to be my matrix. So in this matrix system, I will be storing each and every values. Like if I am encountering f of 3, 5 as a result of something like 2. Okay. Sorry, here comes 2. Okay. Then I will be going to the 2, 5 here. Then I will be changing here as 0. Sorry, as 2. Okay, initially everything will be -1, and whenever I am just finding a result for any function call, then I will be immediately storing in my matrix. If I encounter f of 1, 2 as 3, something like that, then I will be going to f of 1, 2 and making this as 3, like that. Okay, so that whenever I am again searching for that particular element, okay, that particular recursion call or function call, then I don't want to just go beyond that for a recursion. I just take this value and return there. Can you understand this? So that's the main purpose of the memoization. By taking this array, by taking this matrix, I can save my time complexity up to n into w, and my space complexity will be remaining as n into w itself. Okay, fine. So here I am just taking a matrix of size n into w plus 1. So this matrix will be going to be for the previous example I have showed you. this previous example here where for this example, okay, for this example, what is the weight? Weight is up to what? 3, up to 3. And what is the capacity? Sorry. What is the weight array's length? It is 3, right? It is 3. And what is my maximum capacity? It is 5. That's why I'm just making like here 5, up to 5, from 0 to 5 for weight. That's why I'm just mentioning here weight plus 1, the capacity plus 1. And what is going to be my n value? N value will be remaining n value, which means 0, 1, 2 of length 3. Okay, so this is going to be my memoization matrix. So I'll be showing you the memoization code so that it will be more clear. So I can understand. If you don't understand this clearly, you can just watch this code so that you can understand this. It is not much deal. It is basically like I'm just storing some recursion call or function calls result in some memory, and I'm using that once I want that. Okay, fine. Now just see here. So this is the code. So in this code, I'm just taking this lines will be as same as the previous recursion, but here I'm taking a array. Here I'm taking an array of size n into w plus 1. Okay, and filling everything as -1. Fine. Now here I want to check whether the current index and the current capacity's corresponding index is -1. If it is not equal to -1, then I will be returning that current value. Okay, or else I will be proceeding with the as it is, and I will be storing that corresponding result into my index with respect to that current capacity. Can you understand this? So this is as simple as. Fine. So this is going to be my memoization. Now if I submit this code, it will be submitting successfully because its time complexity is what? N into W. Okay, but if I submit that above hash map approach, then it will be not submitting. Okay, fine. Now it's time to go for a tabulation method. For the tabulation method, I will be taking this and explaining you how to convert a memoization technique using array into a tabulation. So this is my memoization code of array, right? Memoization code for array. So from this, I want to convert into a tabulation. Why I'm just converting into a tabulation? Because what is the time complexity of memoization? It is O of n into W. Okay, but its space complexity is O of n into W. So we want to just get rid of this space, right? So the space is of two types. So it is because of the stack space, recursion stack space, and the array. So by using this tabulation method, we will be get rid of this recursion stack space because we are just converting a recursion code into a looping. Tabulation means what? Just we are converting into a looping. Okay. For this, I'll be telling you what is the simplest method. Okay, just to follow. Sorry, this is the arrays code, right? So this is the arrays code. The previous green color is a hash map code. I forgot to paste that. Okay, so this is the arrays code, right? Now in my tabulation also, I'll be taking these all. So let me take that also. So initially it is something like this. Okay, here you should not take -1. If you take -1, it is okay, or you can also take 0, whatever. Okay, in that memoization technique, there is no way we are getting -1 as our result. That's why I'm just differentiating by taking -1. Here you can take -1 in every element or 0 in every element. That's your wish. Okay, so initially I have taken here. Okay, now just go with the base case. So what is the base condition? It is if the current index is equal to the val.length of. Okay, which means we also want that current length value. So I want to again add one more row. Why? Because they have clearly stated in the base case. We have clearly written the base case as value.length of, right? So this is the beauty of changing from memoization to the tabulation. So just listen this carefully. I want to just also add this base condition. So that's why I'm just taking another index called 3 because we want this value.length in my this matrix, right? So 0, 0, 0, 0, 0, 0. Fine, fine. So this is going to be my array hats off now because of this edge case, sorry, this base case. Okay, now we can get rid of this line. Okay, and here comes take another logic. So these all logics will be going into my for loop, So what is going to be my for loop? Actually, you want to do ulta. What ulta? Here, from where you are just iterating for this in this memoization. I will be telling you here clearly in your memoization. Okay, you are traversing the index from 0 to the maximum index or the length, right? While for capacity you are traversing from W up to 0. Yes, in memoization. So that in tabulation you want to do ulta, which means you want to traverse the last index to 0 and 0 to W. Can you understand this? So always remember, whenever your memoization is from bottom up, then your tabulation should be top down. If your memoization is top down, then your tabulation should be bottom up. It should be always ulta. So from this example, I can clearly state that I want to traverse my index from where? Index I from maximum index. So length of val, okay, up to 0. Fine. Inside that another for loop for the capacity W from where? From 0 to that W. Can you understand this? So let me differentiate this by weight. Yes. So this is going to be my first step. And then the next step is just write these 3 lines. Sorry, this 4 lines, up to this 4 lines as it is. So if I write this 4 lines, so int take is equal to 0, weight of array, of index is less than or equal to, here comes weight. We want to modify here as weight. And then next step is what? Take is equal to value of I plus helper, right? Instead of this helper, we are just going to take this tabulation value. So this tabulation value is what? dp, right? This tabulation value is dp. So here I will be taking dp of I plus 1, and then here comes w minus wt of I. So here w is replaced as what? Weight. So here I want to replace as weight. So weight minus wt of I. Okay. So this is going to be my replace here. Instead of this entire thing. I want to replace here. So take is equal to value of I plus dp of I plus 1, and then of weight minus wt of I. Simple, right? Simply you can change like this. And then here also respectively change like what? dp of I plus 1. Again here comes w. That's it. Simple, right? Simple. And then here you can leave this as it is, and you can just leave this line as it is, because take and not take is solved. We already changed here, right? At last I will be returning what? I will be returning the value in the dp of 0 with the maximum capacity. Can you understand this? So this is going to be my return type. You can see here also. Here what I am going to return at last? I am going to return I is equivalent to 0 and w is equivalent to w. So this is what I am going to return here also in my tabulation method. Hope you understand this. And by using this tabulation, our space time complexity will be O of n into w, but our space complexity going to be O of n into w without a recursion space. Okay, recursion stack space is cancelled out. Okay, so this is the time and space complexity analysis. And now let us jump into the code. So see here. So this is the code. So initially my dp array will be what? N plus 1 and w plus 1. I have clearly stated why we are using n plus 1. Because I is equal to length. We are checking, right, in our base condition. That's why I am just increasing my row by 1. Okay. And then here I am doing what? From n minus 1 to I is greater than or equal to 0. So you always do what? Ulta. I have clearly stated that. Okay. So here you can see here. You can see here, right? You are always doing a ulta. If the memorization is like 0 to index, then here it should be index to 0, like that. Okay, that exact thing is done here also. So these two loops are under that condition. Okay, now int take is equal to 0, and if the current weight is less than or equal to the weight, then we want to take that. Okay, or else we will be not taking it. Okay, and then we want to get the maximum among those two, and at last I will be returning. So my kind request is to dry run this particular code by using some example, and you will be surely getting that answer. Okay, always remember, studying DP is way hard. Okay, that's why I'm just explaining each and everything, okay, to make you understand. Now let us go to the next approach. It's a space optimization approach. Why we need that space optimization approach? Because here, what is this? N into W. So we want to get rid of this. So that's why we are going to a space optimization approach. Okay, here whether we want that entire matrix, no, actually no, because see here, dp of I plus 1 and then W is needed. Okay, and also I only need dp of I and W. So almost I need 2 rows of W. Okay, 2 rows of W. Can you understand this? 2 rows of W columns. So that's what I just needed, but I'm just taking what? An entire matrix. So actually, like, we only need these 2 rows for the calculation, because we are just taking what? Either I and I plus 1. Okay, so we need just 2 rows so that we can swap it and we can get use of this. Can you understand this? So that's going to be my space optimization technique. So it is not big deal. I will be explaining here in the code itself because it is so simple. As you see, you can understand this. So basically, just see here. So previous is equal to the weight plus 1. Okay, the capacity plus 1. So this is my 1D array. Okay, and I am iterating from n minus 1 to I is greater than or equal to 0, as I mentioned in the earlier this tabulation itself. Okay, the only change I have made here is this 1D array. Okay, and here again I will be taking a current as a 1D array. Okay, now again I am iterating to the weight and I am taking the condition for the take. Okay, and here I will be replacing by my previous array. So previous array is going to be like dp of I plus 1. Can you understand this? dp of I plus 1 is going to be my previous array, while my dp of I is going to be my current array. Can you understand this? Yes. See here, we only want dp of I and dp of I plus 1. So which means that entire row with the column of capacity length, right? So we only want 2 rows. So in the 2 rows, I will be taking the dp of I plus 1 as previous and dp of I as current. That's it. That's the minor change I want to do in a space optimization. Can you understand this? Yes. So it is, I can just tell you, like, it is hard to understand, but still just realize we are just taking the dp of I plus 1 and dp of I only. So we want only 2 rows. So at last I will be just making my previous as the current. So which means my entire rows value will be replaced to the previous, and again my current will be freshly filled with zeros, so that I can make a process from the last row. Okay, so my kind request is to dry run this code so that you can clearly understand this. Always remember, DP takes time to solve, okay, in your initial learning stage. Fine. So a bonus or additional example or additional approach I want to show you is space optimization using only one array. Just remember in our previous approach, in these particularly in these lines, okay, for this I am just iterating. Okay, Again, for this weight, I want to iterating over all up to the capacity, and I'm checking whether by putting a condition instead of putting the condition inside here. So here itself, I have mentioned a condition. You want to go up to this only. Okay. So once again, I don't want to just check this condition. So I can directly take the value as value of I plus dp of weight minus weight array of I directly. I don't want to check. Okay, that's why I am directly putting here. Okay, so this is going to be your bonus approach. Okay, so what is my time complexity now? The time complexity will be for the optimized space optimized approach. Let me write here space optimized approach. So here the time complexity will be O of n into w and space complexity will be O of w. So it is pretty much an optimized version, right? So hope you understand this entire code, and this video is lengthy because I want to tell you a step-by-step procedure. If I do a dry run also, it will be taking much more time. That's why I'm giving the dry run work to yourself. Okay, if you cannot dry run or you cannot understand a particular topic, then just comment in the comment section. I'll be explaining in any other videos or explaining in the comment section too. If you really like this video and subscribe to my channel, don't skip any videos in the Zoho playlist because all videos will be important. Okay, and also this DP is hard to understand, so don't get demotivated. Thank you.